This lecture is about current division. So first I'm going to do a brief lecture and then do a quick example. So getting started right away, when we have multiple resistors in a parallel connection, so these resistors are in parallel, the source current will be divided into each parallel branch according to KCL, which is Kirchoff's current law, or also known as Nodal Analysis. Now just to review, the Kirchoff's current law, or KCL, is IS equals I1 plus I2 plus I3, or the amount of current going in has to equal the amount of current going out. For example, if this is one big node, here we have this going in, which we could write as 0, because all these have to add up together to get 0. So if you have a 0, which is not IS, but we have IS going in here, so I like to have IS equal a negative number. So negative IS equals, so that's going in here. We have I1 coming out, we have I2 coming out, and we have I3 coming out. Sorry, this is plus. So we have IS going in, which we have the negative IS. Then we have these three coming out, which is positive, which you can choose any notation. Again, I just like having going in to equal negative and coming out to equal positive. So we have plus I1 plus I2 plus I3. And then rearranging that equals this equation. That's just a brief KCL. Let's see. Now that we've gotten this equation down, I'm going to rewrite it down here. So IS equals I1 plus I2 plus I3. Now we're going to analyze each one of these. So remember, V equals IR. We're rearranging it. I equals V over R. Important to remember those. So what we're going to do now is reevaluate these I's. So we're going to bring these I's down. So IS equals, now IS here, or I1, equals V over R. So we're going to have this, for this, that's going to equal V in this circuit. And your voltage is going to be the same across each one of these branches because they are in parallel. That's important to remember. Again, the voltage is the same, the voltage drop is the same for each branch because they are in parallel. So your V is going to be the same for all of them. You could rewrite plus minus V for each one of these branches, but for now we're just going to do it here. Just remember, again, voltage drop is the same for each branch. So rewriting this equation with this notation, we're going to have V over top of R1. So I1 here is going to equal V divided by R1. Moving on to I2, again, we're bringing the sign down with it. So if you wanted to, you could put these parentheses around. So I2 is here. Again, we're going to have this voltage drop of V divided by R2. And the same thing for I3. Here. Rearranging this just a little bit, we're going to have IS equals V times 1 over R1 plus 1 over R2 plus 1 over R3. So this is just rearranging. So we evaluate the circuit here, and now these steps are just plugging in these things that we know. And then rearranging it one more time to get V. We want to know what V is. So V is going to equal, this is just again rearranging your IS over top of 1 over R1 plus 1 over R2 plus 1 over R3. Alright. So writing this in a more general form, so to find a current in one of these resistors, we're going to say that that is going to equal IN. So IN is your current flowing through the nth resistor. So that's going to be represented by IN equals, and then remember I equals V over R. So V over Rn. And here we've already found V. So we're just going to plug that into here. So that's going to equal your IS over top of 1 over R1 plus 1 over R2 plus 1 over R3. All of that times 1 over Rn, like that. Now, this is one of the equations you would want to focus on when you're trying to find IN, but if you're trying to find your voltage, so that'd be this number right here, the voltage drop, you'd be using this equation. But if they're asking for IN, the current flowing across one of these resistors, you still have to find V. So just know what the question is asking. But again, this is IN. This equation is. Now, this is going to be your, next we're going to write our general equation. And that's going to be equal IN equals your IS over top of the sum of 1 over RTP, which here represents to me that resistors, your total resistance in parallel. So again, when you're doing current division, it's with resistors in parallel. So I like to do RTP for total resistance in parallel. And then times 1 over Rn. So that's your general equation. Next we're going to do a quick example. So this question, here we have, just reviewing, is a 10 amps here as the current source. We have a 2 ohm resistor here, 2 ohm resistor here, 4 ohm here, and a 5 ohm here. We see that these are in series and these two are in parallel. So that's just a quick overview of this circuit. And we're trying to find the current flowing across each resistor. So right away you can see that this resistor and this resistor are in series, connected to this current source. Therefore, we can find IA and IB very quickly because they are in series with this current source. The current flowing across these two are the same as the current source. So the current flowing across this 2 ohm resistor is going to be your 10 amps, and the current flowing across this resistor is going to be also 10 amps. But when it comes to here, it's got to decide how much goes into which branch. And that's what this equation is trying to find. So these two resistors are parallel, and the current will be divided into these two branches. So let's look at our equations that we have. I'm going to bring this back. And for this one, we're just going to need this general equation. Okay, so we've already found IAB and IA and IB, so now we still have to find IC and ID. So to do that, let's look at this equation, and let's look for IC first. You can do either first. I'm just doing IC for now. So first you need according to this general equation, you need your IS, which here is going to equal this 10 amps right here. So IC equals, this being IC, equals your IS, which here is 10, divided by, now here we have the resistors in total in the parallel. So you're going to want to look at these two here. These resistors here for your equivalent resistance, or as I like to call it, the total resistance, but only in the parallel ones. So remember, when you're doing resistors in parallel, it's 1 over R1 plus 1 over R2. So we're going to do 1 over 4 here plus 1 over 5, which represents this one. And then times, going back to our equation, 1 over Rn. So because we're looking for I of C, that's across this resistor. So you're going to do 1 over 4 because this is the 4 ohm resistor here. Now plugging this into your calculator here, you can have 10 divided by 1 divided by 4 plus 1 divided by 5 times 1 divided by 4. And switch that to a fraction, and that's going to equal your 50 over 9ths, 50 ninths, or 50 over 9. And again, this is current, so it's in amps. So that's your answer for IC. And finally, let's do the same thing for ID. And it's going to be the same exact thing as what we did for IC. So you're going to look at your IS, which is, again, your 10, divided by your R total in parallel, 1 over 4 plus 1 over 5. Again, all this is the same. It's the same equation there. And times, now here's where it's going to change. So this 4, again, we got from this one, but now we're looking for the the current across this resistor. So you're going to do 1 over 5 here. And then, again, plugging that into your calculator. 10 divided by 1 divided by 4 plus 1 divided by 5 times 1 divided by 5. Change it to a fraction, and that's going to equal 49ths. That's in amps. And that's how you find the current flowing across each of these resistors.